Hi, everyone. Thanks for coming, and welcome to another talk in our ECE Colloquium series. My name is Matt Reynolds. I'm Associate Chair for Research in ECE, and it's my pleasure to introduce Jonathan Lynch from HRL Laboratories in Malibu, California. Jonathan escaped the fires last week and has come up to sunny Seattle to give a talk here. He received the BS, MS, and PhD degrees from UC Santa Barbara in the area of quasi-optical power combining for continuous wave and pulsed millimeter wave sources. And since then, he's been employed by HRL Laboratories in Malibu, where he's a senior scientist in the Sensors and Electronics Laboratory. For those of you who have not heard of HRL, HRL is a corporate research and development laboratory that's jointly owned by Boeing and General Motors. And it's also the place where the first working laser was built in the early 60s. Jonathan's areas of expertise include microwave and millimeter wave antennas, filters, and circuits, and as well as nonlinear components and subsystems such as synchronized microwave oscillators and quasi-optical power combiners. So thank you for coming, Jonathan.
Yeah, thank
welcome.
You, yeah, thank you very much. Yeah, and thanks to all of you. I really appreciate your spending the time to listen to me speak for the next hour or so. And in fact, my goal is to not put any of you to sleep, so hopefully I'll be successful with that. Now, my talk is going to be on digital beamforming techniques for millimeter wave radar imaging. And I'm really happy to give this talk because I'm kind of pulling together material that I've researched and developed over the last probably 8 to 10 years. And it's nice to pull that all together into one place. As Matt mentioned, HRL Labs, it used to be the Hughes Research Labs, but we're not part of Hughes anymore in Malibu. We're owned by Boeing and General Motors, so a lot of these techniques I'll be talking about are applicable to both those companies, especially in the area of autonomy. Autonomy is really important to Boeing and GM. Boeing for landing rotorcraft, for UAVs, avoiding colliding with each other. General Motors, of course, for autonomous driving. So here's an outline of my talk. I'll start with a motivation, a few charts about what are the current hot applications in radar imaging. And I'll also pose some questions that we might try to answer through this talk. There are questions that sort of popped up again, maybe over the past 8 or 10 years to me, that I think are interesting, and in my talk, hopefully I'll answer those. A big chunk of this talk will be multi-port antenna theory. And the idea is present new ways, at least I think they're new. It's hard to find any new things in antennas since they've been around for 100, 150 years or so. But new ways to think about and analyze multi-port antennas. So it's really, I think, a generalization of beamforming from what we learned in antenna theory with these ideal, e to the j, nkd, sine theta, cosine phi kind of element patterns. Those are highly idealized, so this is a much more general way to analyze these. I'll talk about radiation modes that lead to equivalent circuits for antennas, which include the radiation field. And then talk about some generalized beamforming and beam shaping techniques for multi-beam antennas. It's really good for digital beamforming, and you can use this for side lobe control. And then I'll talk about some applications where I'll use some of that theory on a couple of programs. One is automotive for General Motors. Coated aperture radar is what CAR stands for there. And another is a defense application. This is a DARPA program called ASTIR from the STO office. And so starting with the motivation, as many of you know, radar can see through fog, dust, and snow, quote unquote degraded visual environments, DVE. The rotorcraft problem here is a very, it's been around for a long time. When rotorcraft land, they kick up all sorts of dust and the pilot can't see. Security screening is another important one. These are actually, I think, X-ray images, but the point is that what we would really like to have in radar imaging are sensors with angular resolution that approaches what you're seeing there with X-ray. Very, very high angular resolution. And of course, since radar can see through clothes, you can see embedded objects on people. And then the GM application, of course, is automated driving. You know, the goal here, I guess, is as you're being driven to work, you can check your Twitter feed. You know, that's what we all aspire to. And again, I think a common thread here is that for the autonomous driving case, you need to look over a very wide field of regard with very high angular resolution. And it's a very difficult problem, and it needs to be done inexpensively. So angular resolution, as you know, requires a large aperture. The resolution, or the beam width roughly, is approximately the wavelength divided by the diameter of the aperture that you're looking at. So that's one of the reasons it's good to go to higher frequencies. Lambda gets smaller, so you can see a smaller angle. And if you look at, you know, this I think is was done by Kinetic company in the UK. So you can see how large this imager is on top of a car. So you'd like to make this thing much smaller, go to smaller wavelengths. And the other really important thing is cost. For automated driving, you know, GM can't afford millions of dollars for radar sensors. So there needs to be new techniques, and computational imaging is you know, shows some promise there. You need high resolution over a wide field of view. The number of RF channels you typically need is approximately equal to the number of diffraction limited beams in your field of view. So again, if you have 1 degree kind of resolution and you're looking over 100 degrees by 45 degrees, it's thousands of beams, and typically that means thousands of channels, unless you use something like sparse arrays, and you know, that will cut down on the number of channels, but you still wind up with a lot. There's some new CMOS radar ICs by places like Texas Instruments that we're working with. Each chip has 3 transmit, 4 receive channels, so you know, it's not very many, but the chips are about you know, maybe $100 each. So the question is, how can we realize thousands of beams inexpensively? And that's the problem we've been working on at HRL. So as I mentioned, over the years, I came across some problems that I was pondering, and I wouldn't be surprised if there's, you know, some people in this room that probably know the answers to all these, but I certainly didn't. One of the questions is there a way to rigorously treat antenna beams as ports? And being a double E, I like to kind of boil things down to circuits because they're easily manipulated. And it seemed obvious to me if you had, or at least intuitive to me, if you had an antenna array that produces beams in different directions, that you might represent those beams as ports. And it turns out you can, and I'll show you how to do that rigorously. Another question is, what's the physical explanation behind the lambda squared over 4 pi factor for effective aperture? That, you know, I've seen a lot of derivations in books where they use reciprocity. They show that there's the receive effective aperture is proportional to the transmit gain, and then they show it's the same for all antennas, and then they take a specific case that's easy and get lambda squared over. You know, is there some other physical way to interpret that? And I'll touch on that in a bit. The third point is that antenna theory is not exact. And, you know, when we learn beamforming in class, it's, as I said, e to the, you know, j nkd cosine theta sine phi. Well, element patterns don't really behave like that. That's not exact. It's an approximation. Some antennas are pretty good. Some don't even, you know, some aren't even arrays, so they don't conform to that. And so how do you treat a general multi-beam antenna? How do you do beamforming? You know, I'll touch on that. And then lastly, how many beams will a given multi-port antenna produce? And it's not just the number of elements. If you shrink the thing down and there's lambda over 8 spacing, you get far fewer beams that you can produce. So hopefully I'll answer all of these in the course of my talk. And you know, these aren't just interesting questions to me. I really needed answers to these so I could produce sensors, you know, over the past few years. So I'll start talking about multi-port antenna theory and equivalent networks. And what we're seeking here is an equivalent network for an antenna array that not only describes the waves that are, you know, incident and bouncing off the input terminals, but also the patterns that are radiated in the far field. And this will be a far field representation. So how do we find equivalent voltages and currents for the far field radiation? I use a scattering representation. I think it's very convenient because we deal with scattering parameters all the time. And so what we're after is a scattering matrix where each of these is a submatrix. S11 is actually a submatrix that is defines the reflections at the terminal ports. So that's what we're used to when we measure an antenna. And S22 is actually, if you have far field radiation coming in, what gets scattered away in what's called the antenna mode scattering. S12, therefore, is you have a far field wave coming in, what gets back and received by the terminal ports. And S21 then is if you have incident waves on the terminal ports, what gets radiated away. So we're seeking that kind of equivalent circuit representation. And the first question you come up with when defining radiation ports is, what do you mean by a port? Well, what makes a good port is isolation between the fields in the different ports. So coax is really good. Microstrip is good. Waveguide is good too. You can define equivalent ports for waveguides because the fields are orthogonal. And it turns out that what's important is that power flow independently between the ports so they don't interfere with each other. If you have coupled microstrip lines, you wouldn't define the ports as voltages and currents on each one of the lines because they're coupled together. You define usually the even and odd modes. And the reason is orthogonality between the fields. And you do the same thing in the far field. If you have two antennas here, we'll define far field ports by looking for orthogonality between the radiated fields. So the way you do that is you measure what I call or many people call the active element patterns or embedded element patterns, which means if I put incident energy in one of the ports, say the nth port, I get some far field. And so you get, if you do that one at a time with all of the other ports terminated, you get this set of electric fields, and then you form a matrix that's the overlap integral of all those fields. You diagonalize that matrix, and what the U matrix, the eigenvector matrix, gives you the excitation coefficients that give you these radiation modes. And it produces a set of orthonormal modes, and each one of those radiation modes can be represented as a port rigorously. And so you can pull that into Matlab and do computations with them. So it's pretty convenient. So the net result is that an n-element array, if you have n ports, you get n radiation modes, always. And so on the transmit side, what you wind up with is, if you excite the nth input, if you excite all of the inputs so that you get the nth radiation mode, then you have an e to the minus jkr over r, you're in the far field. You have this angular dependence for that mode. And then there's just a certain mode voltage or mode current. And the impedance of the modes is just 377 ohms. It's 8 or not if you're in free space. So that's a rigorous description of the antenna. The S matrix, and again, these are those four submatrices, plus these mode functions completely define all the scattering properties and the transmission and reception of the antenna. These mode functions are orthonormal. They're defined that way. So the directive gain for each of the modes is just the magnitude squared times 4 pi of those mode functions. Now, each one of the modes has an efficiency associated with it. So when I put power in, if the efficiency is really low, most of that energy is going to get reflected back and not much makes it in the far field. And that's actually what superdirectivity is. When you have very closely packed antennas, say lambda over 8 spacing between the elements, you find that many of the modes are very low efficiency. So it requires, if you have 1% efficiency to get a watt out, you need to put 100 watts in. And that's actually the superdirective problem. So the modes form a complete orthonormal set. It accounts for all the mutual coupling, extraneous scattering, mutual scattering. It also accounts for polarization. And what's really nice is that this model's derived directly from the measured fields of the antenna or simulated. So it ties directly to measurements. On receiving, the model is, of course, you have the same modes, with a conjugate, and you have an e to the jkr over r, so these are inward spherical modes. The theta phi dependence is conjugated, and that's just the time reversal of the electromagnetic fields. So if you have a plane wave coming in on the array, what you do is you represent the plane wave as a superposition of these and solve for these mode amplitudes. And when you integrate the plane wave function with this theta phi dependence field pattern, you can actually solve that using the method of steepest descents. And it pulls out of the minus j lambda out front. And then the plane wave vector amplitude dotted with the mode function. And that's the amplitude. And if you actually, the result is proportional to wavelength because you're integrating this plane wave dotted with a spherical wave. And so when you use the method of steepest descents, those phases match over kind of a small region right here. The smaller the wavelength, the smaller that little region is. So when you do that integration, the result is proportional to wavelength. And when you use these results, you get the effective area, the maximum effective area of the antenna is lambda squared over 4 pi times d. So that kind of at least gave me an idea of where that lambda squared comes from. Because I'm representing that plane wave as spherical wave functions, the area of stationary phase is proportional to wavelength, the area to wavelength squared. And that leads directly to an equivalent circuit for the receive array, where this is the voltage source amplitude. So again, this lends itself to computation in Matlab. So the next concept I'll kind of introduce, I think is very useful, are transformation networks. And so if we're trying to, I mentioned there's an excitation for an array that produces a certain radiation mode. I can produce that with a network. And this network I put in front of the antenna array, and it has this scattering matrix. So S11 and S22 submatrices are 0, so they're perfectly matched. S21 and S12 are a unitary matrix. So this is actually a unitary lossless reciprocal network. So this is a physically realizable network. Although in practice, we typically wouldn't design these, although people have. They tend to be very complicated. This is really useful for digital beamforming, and I'll get to that in a bit. So when I place this in front of my antenna array, the net scattering matrix for the antenna, these get transformed by this network. S21 and S12 get diagonalized. And that's the idea with the radiation modes. When you now excite incident energy on one of these ports, I produce one of those modes, and they all are non-interacting. So the upshot here is that these radiation modes are what diagonalize the S21 and S12 submatrices for the more general scattering matrix for the antenna array. Now it turns out S11 and S22 generally don't get diagonalized by that same matrix. For the lossless antenna, if this is totally lossless, then S11 and S22 also get diagonalized, but that's sort of a non-physical case. No antenna is perfectly lossless. So these are really useful tools in array analysis. And again, it gives me a circuit description of the antenna that I can use in computation. I can also decouple effectively get rid of the mutual coupling between these ports through a different diagonalization that diagonalizes S11. But it depends on your application, but that's usually less important than utilizing the radiation modes. This just gives you kind of a pictorial example of a 5-element array. I just simulated an HFSS, 5 dipoles. These are the 5 different radiation modes. I believe this is the broadside mode where all elements are more or less in phase. Again, it completely takes into account mutual coupling, mutual scattering. And some of the higher order modes are kind of funny looking. I think these were, they were lambda over 2 apart, if I remember correctly. And so all of these 5 modes have reasonably high efficiency because the spacing is far enough. So that leads me to this concept of degrees of freedom for an array, where, strictly speaking, an array has as many complex degrees of freedom as it has terminal ports, but not all of the modes are equally accessible at the terminal ports because of the mode efficiencies. And so I've shown some plots here. This is simulated 5 lambda over 4 space dipoles, and these are the mode efficiencies. So like 3 of these modes are very efficient, 2 of them not so efficient. And so as you pack these things closer and closer together, you lose the efficiency of some of those modes. This shows a 32 by 32 array of open-ended ridge waveguides, and that's actually a case I'm going to bring up later that we actually built and tested. But you can see here that most of the modes are fairly efficient. These were actually designed to be mismatched for reasons that I won't go into here. But then we probably only have a reasonable efficiency for about 800 out of the 1,000, 1024 modes. And that just has to do with mutual coupling. Mutual coupling tends to reduce the number of modes that are efficient. Now, these are from measured data. This is a 32 by 4 electronically modulated receive antenna, measured data. There should be about 128 modes. We have probably about 70 modes here that are reasonably efficient. And I'll talk about that later too. And this is the 1,000 element array measured. There's not very many modes here. One of the reasons is that we measured over a restricted field of view. And when you do this computation, these overlap integrals over a restricted field of view, you then essentially count the number of modes that are within that field of view and excluding outside of that. So that's another kind of handy thing. So the degrees of freedom really determine how well an array maps the terminal port excitations to the far field. That's one way to look at it, it's that linear transformation. So just in summary of this network approach, the more general scattering matrix that I've introduced, plus the mode functions completely describe the transmission, receiving, and antenna mode scattering properties of an array. It's described by an equivalent network, so it's easy to compute with. The radiation modes are described by mode functions and also the receiving modes. And if you want, you can decouple the terminal ports of the antenna. All of this, by the way, is in a paper that I published a few years ago that I can give you a reference to. So the next thing I'm going to be talking about is how to do beamforming and beam shaping using some of these concepts. Now I'm going to switch gears a little bit, and I've talked about modes, but now I'm going to no longer talk about modes. I'm going to use the embedded element patterns of an array, which are these E sub n functions. They're typically vectors, but I'm going to do a scalar treatment here because it's simpler. So when you have an antenna array and you put energy in one of the ports, the far field you get is this E sub n of theta phi, in the far field with an e to the minus jk over r dependence. So as you put energy in one port, you terminate all the others, and you get these embedded element patterns. So again, this includes mutual coupling and scattering and things, and normalize them properly. In fact, I normalize them so that the magnitude squared times 4 pi gives me the gain of that element pattern. What we do when we beamform is just take these element patterns as a basis and form linear combinations to form beams. And so we multiply by a weight, and in fact, in a very convenient notation that I use is to use the A sub n as the incident wave amplitude, from a scattering description, so that when you form these weights, it's just the A sub n multiplied by that element pattern gives you the far zone field with the e to the minus jk r over r suppressed. But this is just a linear combination of these things. The realized gain pattern then is the magnitude squared of the electric field divided by the incident power. So, and the realized gain, I think, is the most useful gain function because it includes any reflection off the input, which is real power loss. It turns out that to maximize gain in some direction, theta 0, phi 0, you just choose the incident wave to be the complex conjugate of the electric field in that direction. Now this thing that I've shown here is a vector. So this is a vector of incident waves. And it's just the conjugate of whatever the element pattern fields are in that direction. So when you compute the gain, G max, it turns out it's the sum of the element gains in a particular direction. That's the maximum gain that you can achieve. And that maximum gain function, it's a function of theta 0, phi 0, is very useful. It's a useful concept because in a multi-beam array, you can produce you can put a network in front of this thing to produce many beams in different directions. So one of the questions is, how do we choose the weights that maximize the beam gain in any direction, which we answered previously, but how do we do that for multiple beams within the array? Can we choose any beam directions we want? And the answer is yes, but if you space the beams too closely together, you're not going to get very much gain in that direction. So what's the minimum number of beams that are required to completely fill the field of view of this thing? And to answer that, I'll answer that in the next few slides, we first have to figure out what we mean by the field of view of the array. And the maximum gain function that I discussed in the previous chart, I think, is the answer. Because the field of view is a convenient way to describe it. Where'd my mouse go? Mouse disappeared. Here it is. If you look at that maximum gain function as a function of what direction you're looking, it's the maximum gain that you can produce with any beamformer. It's just the sum of the magnitude squared of the element patterns in that direction. It turns out that the maximum beam gain function is independent of the beamformer as long as its transformation network is lossless. So what I mean is I have an antenna array, I put a transformation network in front of it. Again, it has this type of submatrix description. So there's a unitary transformation of this thing. So if I put energy in one of these ports, that U matrix produces all of the inputs at the antenna ports that give me maximum gain in a certain direction. Now, it turns out that when I can choose whatever unitary matrix I want, and when I calculate the maximum gain function back here at these ports, it's still the sum of the element patterns of the original array. So I can choose any U matrix I want, and that maximum gain function is completely independent of the choice. And I'll explain why that's important in the next couple of charts. So here's an example of an 8-element patch array simulated in HFSS. It includes a plastic radome on top, there's mutual coupling, et cetera. The cut in the XZ plane here is nice and smooth, as you'd expect. But in the YZ plane here, because of all the scattering and the mutual coupling, it's pretty ragged. And so the question then is, how do we find a unitary set of beamformer weights that produce directional beams for this? And the answer is, what we do is we determine the set of weights for one beam direction and then form the next beam using all the weights that are orthogonal to that one and keep repeating. So I'll kind of walk you through that. So here's my 8-element array. I'm choosing a beamformer network here that produces a beam in 5.5 degrees in azimuth. So here's the main beam. So this network has a matrix U1 that when I put energy in this port, it creates all of the incident waves necessary to produce this beam. And the way I figure out what that U matrix is I take the vector of element patterns in the theta 1 direction. I form this outer product. This is a matrix. It only has 1 degree of freedom because it's an outer product. It has an eigenvector matrix U1 that's unitary, and that's what this submatrix is. There's only one non-zero eigenvalue, and its eigenvector is this quantity. All the remaining eigenvalues, and by the way, this produces the beam in that direction. If I put energy in any other one of those ports, it produces a null in that direction, theta 1. And so you can see that the energy comes up and it hits that maximum gain function, because that's the maximum gain that I can possibly produce. So it achieves that. And so the first beam will always have maximum gain. So then I go on to the second beam, and the way I do that is I just terminate this port and treat this as an n-1 element array and go through the same procedure. I choose another beam direction, which I've chosen actually to be the null in the first, so that I can hit that maximum gain function. Because remember, in the end, the maximum gain function is just the sum of the magnitude squared of all these beams. And so I then produce another beam here, and energy in all of these ports produce nulls in those two directions. And I can just keep going. So I can construct a multi-beam antenna, and here it is, for all of the 8 beams. Each one of these is a lossless and reciprocal network. So the concatenation of all these things is a lossless reciprocal network. So I have my unitary transformation for all the beam weights. So the beams have the maximum gain or the highest resolution possible for the number of degrees of freedom that are available to it. They completely fill the field of view. The magnitude squared of all these, when I add them up, is the maximum gain function. And so this defines how many beams that you can have in your antenna. So the number of beams is the same as the number of antenna ports, but because the mode efficiencies are not all, generally speaking, they're not all going to be 100%, what you find is that the last few beams tend to be kind of not very directive and not very useful. So as I said, in practice, you wouldn't really make this in hardware, but it's really useful for digital beamforming, and I'll go into that next. So beam shaping. Side lobe control is important. We all learned about Chebyshev and Taylor distributions and all that kind of stuff. They're all for ideal non-interacting elements. And one of the problems that I had in designing antennas was to deal with very non-ideal antennas. I mean, there may have been arrays, but they have complex lenses and things in front of them that I'll show you examples of. Adaptive techniques do work very well. I mean, they've been around for a long time. But in any adaptive technique, it's not clear whether the adaptive solution is optimal. And it also, at least in my opinion, doesn't really provide a good understanding of the effects of null placement. What does it cost you, and how does it affect things? So I'll kind of describe how this theory, I think, helps illuminate this. So to place a null, that'll be the first thing. I have an antenna array. I put my beamformer here to produce a first beam. That's shown here. And how do I create a null? Well, let's say I want to create a null at the first side lobe of that beam. I have a second beamformer network, and I produce a beam in that direction, and then I just excite energy in that port that's precisely the amplitude and phase that cancels out the energy from the beam in the first port. And so that when I superpose those two, I produce a null on the pattern. And what's nice about this trick is that it tells you that, well, it allows you to do the cancellation with the minimum possible energy. So it's an optimum in that sense. It also shows you that since I've created the most directive beam I can in the cancellation beam, it's going to affect the beam elsewhere minimally. When I place that null, or when I put that beam, remember that energy in this port still creates a null at the location of the peak here. So as I keep adding nulls, I never disturb the far field at those other points. So they're non-interactive. So it's a pretty straightforward method. And as I mentioned, as you keep doing this, eventually, if you don't have 100% efficiency in all of your radiation modes, the beams that you form down the line are going to be kind of broad, and they will disrupt the pattern elsewhere. They're not as useful. And also notice that each null placement uses up precisely 1 degree of freedom in the array. So this allows you to tally the cost of beam shaping, cost in terms of power. So as I find my mouse, here it is. As I keep adding nulls, and I figure out how much energy I need to provide the cancellation, I think I've added 4 or 5 nulls here and gotten the pattern to look like this. I can tabulate exactly how much energy it cost me. And so in the end, in this example, and this is from simulations, the gain is 92% of the maximum because of the additional power I needed for beam shaping. So this is a really nice way to quantify the cost in beam shaping. And again, for every null, it's the minimum amount of power required. Okay, so that's it for the theory. And I'll talk about the application of some of these concepts to radar imaging. So these are actually systems that we developed at HRL. The first one of which is a W-band coated aperture radar. I'll explain what that means for automotive. And okay, so I'm not going to go through this chart in detail, but what we need is high angular resolution, low cost. Coated aperture radar, that I'll explain in a minute, is a way to do that. We do pay a price with sensitivity, and it's just a simple energy problem. But what we get is low latency and wide field of view and hopefully low cost. So the way coated aperture radar works is we have a single FMCW transceiver. And this shows aperture coating on receive only, but you can do this on transmit too. And in particular, in our case, we had a lens that I'll show you some details about. So it's kind of a complicated front-end optic. Behind each one of the receive elements is a phase shifter. But the phase shifter has only 1 bit. It's either 0 or 180 degrees. So in like many computational imaging schemes, as we frequency step up, at each frequency step, we have a different set of pseudo-random states of the phase shifters. So you get a whole bunch of pseudo-random antenna patterns, receive patterns here. We sum all them down to a single port, and with one A to D, one IQ A to D converter, we record everything that comes through due to all these different pseudo-random states. And there's typically a whole bunch of these ramps in a row to get Doppler information. So you do range Doppler processing. So the idea is that you record all this information and then process it for range rate, and bearing estimates using match filter processing to get good angular resolution as well as range and range rate. This shows a block diagram of the system we built. It's kind of a gold brick design, and as we had talked before, I did that on purpose so that I can break this system and measure and characterize all these different blocks, rather than having one chip that puts out A to D bits that I don't really know what's going on inside and can't modify it. And as I mentioned, so I'll show you some details, but we have an antenna array with single bit phase shifters. All the outputs get summed to a single channel, and there's a lens in front of it. And the lens is for, in automotive radar, you tend to want a narrow elevation field of view. Usually fairly wide in azimuth, narrow in elevations that you don't see the road. So we did what we call a folded reflector antenna design. So this shows a cross section of it. So this is a side view. So this is actually the elevation direction. So the beam gets narrower in that field of view. There were 4 patch elements at the bottom. They're about roughly λ/2 spaced. And this is, again, at 79 gigahertz. They're aperture coupled patches. So this thing actually extends along this. So there's 32 of these 4-element columns. So it's a 32 by 4 array. Now, we weren't able to simulate that whole thing in HFSS because it's a really big problem. So I simulated just one of these slices of 4 patches because, again, it's uniform in the other direction. So we do digital beamforming in azimuth, and then in elevation, we narrow up the beam and do actually more digital beamforming. So the way this works is, this is on receive, so the energy comes in, and there's a metal grating on the inside of this top reflector. It's called a transreflector. So it passes one polarization. And then it comes down and it hits this twist reflector surface. It's a grating designed at 45 degrees. So what reflects off, the polarization twists 90 degrees. And you can see it's also curved, so there's some focusing. The energy goes back up, hits the transreflector. Now it's orthogonally polarized. It reflects back down, and again it's curved, so it focuses down onto the patches with the correct polarization. So we designed all this. The reason for doing that is it's a focal plane array. If I didn't do that, it would be 3 times the depth, so this is a way of making it compact. It's a factor of 3. And you can see the simulated elevation pattern, and the measured actually even came out better than simulated, which rarely happens, but it happened in this case. So there was good gain in side lobe performance. And again, this thing is uniform in azimuth with 32 of these things. So we used a digital beamforming approach. And so this is an example where I have a very complex antenna. It doesn't really look like an array. And so how do you do beamforming? Well, we did a lot of calibration of this thing. So we put a corner reflector in an anechoic chamber and then moved the sensor in different orientations. So for each orientation, we transmitted a whole bunch of these codes and recorded all of the information, the I and Q data. And then we moved to the next position and did this. So there's an enormous amount of data in the calibration. And then, in essence, you can do a match filter processing to determine the location of scatterers in the far field. So one of the things we did, we took all that calibration data, and if you form a matrix out of it, you can do a singular value decomposition. It tells you, again, how many degrees of freedom is in the array. And that's the measured data I showed you earlier. And there's about, instead of 128, which there are elements, there's probably about 70-ish significant degrees of freedom here. Part of the reason for that was there was probably about a 50% aperture efficiency. And as you move over in azimuth to some of the side elements, the efficiency even drops because there's the side of the antenna kind of gets truncated. So that's kind of roughly what we expected to see. And then we did beamforming. And what's interesting here, actually I'll back up a slide, is that we now have a case where as you step through all these pseudo-random codes, each one of those, of the information that you record for each one of those codes, that cumulated set becomes your basis for beamforming. And so it's, again, a generalization of the idea of beamforming. So we're forming linear combinations of all of those different complex patterns produced by these pseudo-random codes. And so we use the same techniques that I went through before, but instead of element patterns, these are actually due to the codes. So these are some of the results. It just shows some of the beams, azimuth and elevation. So in azimuth cut, because I have 32 elements, I could actually do some nice beam shaping and get like 18 dB side lobes. In the elevation cut, I only have 4 elements. I couldn't do as well. It actually cost me a lot of energy. But I got them down to about 13 dB side lobes in elevation. So that's kind of an example of using these techniques, generalized beamforming and beam shaping for a real-world problem. And this shows all of the azimuth patterns. There's really about, if you exclude these funny-looking things on the side, I think there's about 16 beams. Times 4 is 64, so that's roughly half of the degrees of freedom that of the maximum 128 that I had. Okay, and now I'm going to switch gears a little bit and talk about a DARPA program called ASTIR. It's a 235 gigahertz, and I can see that I'm kind of running out of time, so I want to leave time for questions. So we're building an electronic subarray using coded aperture radar, single bit phase shifters behind each element, single transceiver. So all of the switching, it's a reflector array now, so it's a little bit different. And so the way we built this, these are open-ended ridge waveguides. There is a device at the bottom that's a GAN hemped. So we can control whether the device is on and off, and that, if designed properly, gives us the 180-degree phase shift. It's nice because this whole thing is fabricated, and I'll show you some photos, but it's fabricated at kind of the wafer level, and the control of the gates of the hemps is actually on the back side of the chip. And then we have ASICs down here that switch all these things on and off. So it's very scalable. One of the difficulties here is because of all the mutual coupling and mutual scattering, the devices all interact. So to get an accurate simulation of this thing would require HFSS, and actually I modeled the devices in HFSS too, because they're essentially passive. But because of all the mutual coupling, I would have to model devices on and off in all of those different combinations. So I used the theory to develop an equivalent circuit for this thing, where I could then attach all the devices and compute the reflection coefficient of the whole thing. The TR module that I had illuminated has a scalar feed horn with a approximately Gaussian beam kind of distribution. And it turns out the incident waves, you can use these mode functions and integrate over this Gaussian function to get the set of modes that's incident on the array. So everything, all of that, the point is that it's easily handled in Matlab and much, much, much faster. I do one HFSS simulation for the array, and the rest is just computation. So we fabricated this in a silicon wafer, silicon micromachine. These elements are about 700 microns apart, which is about half a wavelength. Open-ended ridge waveguide. The whole thing is metallized after. And we got excellent accuracy, like nanometers of accuracy for the ridge gap, which is kind of the most sensitive dimension. And this shows the tile assembly. These mimics are bonded down to the silicon micromachine ridge waveguides. The gate control is fed through to the back of the mimic, so that's where the electronics attaches to. Looking down into the waveguide, here's the GAN chip in the bottom. So this is all very scalable. And here's the arrays face up. So we broke out all of the gates to pads on the outside that we then connected to analog switches to control the phase shift states. To measure this thing, we mounted this device under test on a positioner. We had a receive horn that's nearby. It was only about an inch away. And then in the far field, which was maybe 3 or 4 feet, we had the transmit horn aimed at it. So then we'd move this thing on a positioner in 2 degrees of freedom. We were very limited in all of the angles, especially in elevation, because the thing was kind of clunky and not balanced very well. You can kind of see it here. And we measured a bunch of, we measured copper block for gain calibration and measured a small array and a large array. And then we did beamforming. And again, using the same techniques that I presented here. It's kind of interesting in time, when you look at the IQ output, you're switching through all of these different states. And you can see, the INQ little kind of stair steps, pseudo-random. Singular values, there were about maybe a couple hundred, maybe 150. Again, we measured over a narrow field of view, so they're, it's not the whole, 4 pi. And these, again, these codes we use as the basis functions for beamforming. And so these show the measured pattern cuts in azimuth and elevation. The beams look pretty decent. It turns out after we assembled the whole thing, about half of the elements were not working, and we're not really sure why. And we're right at the tail end of the program and couldn't spend time to figure out why. But we still get nice results, and it kind of shows how robust these things are. Once I had this data, I added a couple of nulls to make what's pretty close to a diffraction limited beam width, and then stepped it across. And of course, this is all digital at this point, so you can put the beam wherever you want. But that demonstrated the ability to do digital beamforming with one of these reflector arrays. So in summary, no, good, I left like 10 minutes worth of questions, but this, hopefully I got across the idea of this sort of general approach to beamforming and beam shaping for multi-port antennas, that it's not just arrays, but in any antenna. And so we now have answers to those questions. Is there a way to treat antennas as ports? Yes, and I went through some detail on that. We have an explanation for that lambda squared over 4 pi, which I found satisfying, but maybe the only one. And array theory is not exact. How do I form beams with a non-ideal array? And you construct that unitary matrix that forms the maximum gain beams. I think that's really useful. The construction may be used for side lobe control, as I've pointed out. And how many beams will a multi-port antenna produce? And it's approximately as many as the significant eigenvalues of the matrix of overlap integrals of those element patterns. And so hopefully, that'll make sense to you folks. And I'm happy to ask any questions.
So any questions from the audience?
Yes?
Will you give us references to the paper?
Absolutely. In fact, I'll send them to Matt, and you can distribute them to whomever, yeah. I don't yet have a detailed reference on the ASTIR program. That will be out on the SPIE in April of next year. I'll be publishing that. But the theory I do, yeah.
We have a lot of students who are very interested in autonomy. And I guess, could you tell us a little bit about how you would translate requirements of a sensor for an autonomous car into the system engineering that you've done for that radar sensor?
Yeah, certainly. And I'll take the case of General Motors. And they actually want as high an angular resolution as they can get. I don't think they've quite figured out how they're going to handle all that data. That's another important part of the question. But the requirements, obviously it depends on which application we're talking about. For GM, they typically want range resolution on the order of, less than a meter, certainly. It's usually a couple hundred, millimeters or so. Angular resolution, they really want the performance of LiDAR. I mean, we're talking about half a degree. And it's over a wide field of view. And when you're thinking about the autonomous driving problem, you want to navigate in very dense areas with people could be running out from between cars. You need to see all that stuff. And it's all clutter. But what is clutter, right? I mean, you need to see everything and pull out what's important in that. Yeah, I mean, when you talk about the requirements, they want as much as they can get for as cheap as possible.
Yeah, so just following up on the degrees of freedom, what you see effectively, do you have a sense of connecting? So you gave examples with the 128 beam array, you get 64.
Yeah.
It's a function of many physical parameters.
It really is, yeah.
So do you have a sense that, function of the field of view, the spacing, maybe near field, scattering?
Yeah.
Can you connect the actual physical deployment to the effective number of degrees of freedom?
Yeah, to a large degree we can. One of the important effects is mutual coupling between the elements. So if they're half lambda spaced, there's a certain amount of coupling that that will reduce the number of degrees of freedom. If in sparse arrays, when you move them beyond lambda apart, you then get that back. I mean, so that tends not to be a factor. Scattering off the radome, that will also couple elements together. Aperture efficiency is really important. And so as I mentioned, we have an array with a lens, and the side elements tend to get blockage from the side of the array. That'll reduce the number of degrees of freedom. All of those things are important.
Great. Any other questions from the audience? All right. Well, let's thank our speaker. Thank you, John.
Well, thank you all very much.